everyone, in this video I would like to share about what I have learned on magnetic circuits. So I think we all know about electric circuits. They use the Ohm's law, which is volt equals current divided by resistance. And magnetic circuits have a very similar principle. It looks like this though. It's magnetic flux equals magnetomotive force divided by reluctance. So I think it's best to explain a little about how electric circuits work first. And as I said before, there are three main components, which are the voltage, the current, and the resistor. Voltage is like this. If you've seen batteries, they have a positive symbol and a negative symbol. If I'm not mistaken, the positive symbol usually have too many electrons, and the negative symbol doesn't have enough electrons. That way, the positive terminal throws electrons into the negative terminal because they want to become balanced. And that pushing force of wanting to throw the electron into the negative terminal is the voltage, whereas the current is the amount of electrons that are being thrown in a second. So the current is the amount of electrons thrown from the part with the more electrons to the less electrons. That is current. And resistance is like an object in between the positive and the negative terminal that is blocking some of the electrons from entering the negative terminal. It is resistance. The same principle applies with magnetic circuit, except it's a bit reversed. The electrons that are being thrown is actually the magnetic flux, and here in the equation it's the pushing thing equals the push things divided by the blocking thing, and here it is the push things equals the pushing thing divided by the reluctance. And yeah, the thing that is being pushed, the replacement for electrons is magnetic flux, whereas the replacement for the voltage is the magnetomotive force. And yeah, it's a resistance reluctance. So magnetic flux, in simple words, have you seen about how a magnet is able to capture another magnet? Well, there are actually invisible lines called a magnetic field. And a magnetic flux is basically the amount of those invisible lines that would still connect to a magnet if there is a wall in between. So like, because of this wall in between, of course not all of the lines are able to pass through. And that lines that are able to pass through are the magnetic flux. And for magnetomotive force, it's basically like pushing that magnetic flux through the magnetic field itself. So in other words, magnetomotive force is just the magnetic field itself pushing the magnetic flux. And our reluctance is basically how good an object is or a material is at receiving those magnetic flux. Higher reluctance means it is worse at receiving magnetic flux. So the goal of this circuit is to find some things. The first one is to find the magnetomotive force itself. The second thing is to find the magnetic flux of the center line. The third one is to find the magnetic flux of the left leg. The fourth one is the magnetic flux of the right branch. I think it's more accurate to say branch than leg. The fifth one is to find a flux density. In the left leg And the last one is to find flux density in the right leg. So first, we have to find the magnetomotive force. The formula to find a magnetomotive force is actually very simple. It's just F equals the amount of coil turns multiplied by the current. And here, as you can see, there are 400 coil turns and there is 1 ampere for the current. Therefore, the magnetomotive force is just 400 turns multiplied by 1 ampere. The answer is 400 ampere turns. This is the first answer for the first question. So our mark it as done. The next question is to find the magnetic flux of the center branch. So this thing is actually a story parallel circuit. If I have to redraw this entire thing in another image, it would look like this. This is basically what this entire magnetic circuit looks like in a simplified manner. And the one on the left, this is the center branch of the magnetic circuit. This one, it can be both left or right, but we'll just assume it's the left one, and the bottom one we assume is the right one. So this one I'll write as the RC for as the reluctance of the center one or resistor, basically it's the same equivalent. This one will be the R left, and this one will be the R right. So in order to find the magnetic flux, first we have to find the reluctance first. And again, as I said, the magnetic flux is like the equivalent of the current. And to find the current, you still need to find the resistance first. So there are two formulas for reluctance. The first one is reluctance for lag. The second one is reluctance for gap. The formula for reluctance for lag is length divided by permittivity of free space multiplied by relative permeability and multiplied again by area. This is the formula for reluctance lag, and the formula for reluctance gap is length divided by permittivity of free space multiplied by area. And it is the formula for the reluctance gap. So this implies that we have to find the area. We have to find the area for the center one and for the left and right leg. So the area in the center is equal to this part. So it's 0. Basically it's 7 centimeter multiplied by length. I forgot to apply length first to the question, so I'm going to get it now. The length is supposed to be 7 centimeters as well. Thus, the area for the center is 7 centimeters times 7 centimeters, which is 49 centimeters square, or 0.0049 meters square. The area for the gap is a bit different though. It's not just like the center. It's actually 1 plus a percentage of fringing. Fringing percentage plus the area from the center. But what is this fringing? So fringing is basically the widening of the magnetic flux line. Basically the line inside this circuit, which is caused by the air gap happening here and here. The result is that the magnetic flux stays the same amount. However, the magnetic field becomes weaker because the area becomes larger. And it also inadvertently decrease the level of magnetomotive force. Written in this formula, fringing will be 5%. So if we assume that the fringing is widening the line by 5%, thus the gap for the area for the gap would be 1 plus 5% plus 0.0049 meters squared. Thus 1 plus 0.05 plus 0.0049 meters squared. I'm sorry, there have been a mistake. It's supposed to be multiplied, not plus. The result would be 0.00545 meters squared. So as I've said before, we can see that the gap area is bigger than the center area. So it's 5 or S minus 4. The next part, we have to find the reluctance for the air gap and the legs. It would be 0.07 centimeters divided by permittivity of free space, which is 4 pi times -7 times the area of the gap. The 0.07 centimeter is equal to 7 times 10 to the 4 result for the reluctance on the left gap would be 108, 268,668 ampere turn per Weber. That is the reluctance for the left gap. The reluctance for the right gap would use 5 times 10 to the power of negative 4 meters instead, divided by the same permittivity of free space, and multiplied by the same gap area. The result is 146,059 ampere turn per Weber. And if I have to explain the fringing effect again, basically this is the regular length. This is the regular area for the center part, but the left and the right area are becomes wider by a small bit. This area becomes bigger. This area gap, and this is area center, and this is area gap. They become bigger due to the hole that are left in between the two legs. So we have found the reluctance from the left gap and the right gap. Now we have to find the reluctance in the left leg, the center leg, and the right leg. To find the reluctance on the left gap, we will have to find the total left leg length of the left gap, subtracted by permittivity of free space times relative permittivity times the area. And as we can see here from the left gap, it starts from here, then it goes here, then it goes here, then it goes here. What we can infer that it started from this point, it goes by half of 7 cm, which is 3.5 cm, and plus 30 cm, plus 3.5 cm, and again here plus 3.5 cm, plus 30 cm, plus 3.5 cm, and again from this part plus 3.5 cm, plus 30 cm, and from this part plus 3.5 cm. So it's 3.5 times again 1, 2, 3, 4, 5, 6. So 6 plus 30 times 1, 2, 3. I think we have to find it in meters first. The answer will be 21 centimeters plus 90 centimeters, which is equal to 111 centimeters or 1,11 meters. And then the reluctance of the left gap would be 1,11 4 pi times 10 to the power of negative 7 times the relative permeability, which we can assume is 1,500. And again multiplied by 0.005145. square. The result of the reluctance from the left gap would be 123,223 ampere turns per Weber, and the right leg will have the same value as the left leg. Because it goes through the same length and it has the same area. So the reluctance from the left leg and the reluctance from the right leg both have equal values. So now it's time to find the reluctance for the center leg. But if the making a mistake this whole time, I should have written L instead of G, because G means gap and L means like. For the reluctance of the center leg, it would be the center gap length with the same formula too, and it will be from here to here. So this is the length of the center leg. So it's 0.35 plus 30 centimeters and plus 3.5 centimeters. So it's will be 0.35 times 2 plus 0.3. I think I should have one 0 here, and divided by the same 4 pi and to the power of -7 times 1500 and times 0.0049 meters squared. The result would be 40,059,4074 ampere turns per Weber. So at this stage we have found the reluctance for the left leg, reluctance for the right leg, reluctance for the center leg, and reluctance for the left gap, and reluctance for the right gap. Now we have to merge all those reluctances to later be implemented in this formula. We have found 400 as the value of the magnetomotive force, and we have to find the reluctance for all of this to find the magnetic flux. I will erase some of this part to make some more space. this stage, we should find the total R to later be inputted into the magnitude formula, which again is analytic flux equals reluctance. To get the total resistance, again, as I have drawn it before, the image should look like this. Therefore, it requires the use of current divider formula. For the total reluctance, first we have to find the left branch. It will be equal to the reluctance of the left gap plus the reluctance of the left leg. And I will skip writing all the numbers because it can be time consuming. The result will be 228,447. And the unit of measurement is ampere turns per Weber. For the right branch, it would be the right gap plus the right leg, and the result will be 197,513 ampere turns per Weber. And due to their parallel nature, when they are combined, they cannot be simply added. They must use the formula of two resistors parallel formula when trying to be managed. So it is like this. One per total R equals 1 per R left plus 1 per R right, because at B for branch. And it will be to better simplify it, we can modify the formula. So it will look like this: 1 per total R will be LM branch, because it will be more specific that we are not looking at the whole reluctance but rather just the branch first. Equals 1 per left branch multiplied by the right branch divided by the right branch plus 1 per right branch multiplied by the left branch divided by the left branch. The ink is dying, so I am going to use another blue marker. The result will be 1 divided by the reluctance of the left branch times the reluctance of the right branch is no longer 1, it's the right branch, plus the reluctance of the left branch divided by the reluctance of the right branch multiplied by the reluctance of the right branch. They have the same denominator, so their numerator can just be added like this. And since it is still the thing that you're trying to find is still the denominator, so we can swap it like this. Thus, the result is I'll make this more clear. It would be 228,447 multiplied by 197,513 divided by the same thing except they are added. the final result of the reluctance of the branch would be 106,000 ampere turns per Weber. Thus, we have found the reluctance of the right branch, and now to find the total reluctance, we just have to add this to this, because as you can see after we use this parallel formula, it basically just makes it look like this. And if it's already series, we just have to add both of them. This one is this one, and the other one is the merge of these two. It's the merging of the two. So the total R will just be equal to the addition of both reluctances. The result will be 46,059 ampere turns per Weber. So this is the total reluctance. We've come to this step to maybe have done about let's say 60% of the homework of this task. And now we can find the magnetic flux in the left line. But we cannot do that first. We must find the center one first, because I'll explain again later. To be able to find the magnetic flux at the center, at the left and at the right, we first have to use the current divider rule. So essentially, the current divider rule is the total current multiplied by 1 divided by that specific reluctance or resistance. I'll change this because it's not by 1, it's by divided by I plus R1 plus I plus R2 plus I plus Rn. So again, I'll explain this current divider formula. Current divider formula is used when we want to find the current from multiple resistors, and then they are placed in a parallel form. So to find a specific current, we first have to multiply the previous current from the previous step, which is basically this center current multiplied by 1 divided by a specific resistance. And this Rn is basically until unlimited amount of resistances. So if you swap around the symbol, it will look like this. Because I basically what the formula would look like to find the magnetic flux at the left branch. And as you can see, we must find the magnetic flux for the center branch first. So magnetic flux for the center branch is equal to the magnetomotive force divided by the reluctance, and it will be 400 divided by 146,059 equal to 2.74 times 10 to the power of -3 Webers. And again, the 400 is found from 400 resistance multiplied by 1 ampere, and the 1459 is found from the total reluctances. And yeah, I will have to erase some more part to make space. We no longer need the information about the specific reluctances at the gap and at the light, but we can summarize it as left branch So now I would like to explain about finding the left magnetic flux. Would be okay, this is the magnetic flux of the left branch, and we have two choices. We could either just calculate it with the calculator, or if you want to simplify the formula, it could be done this way by simplifying the current divider rule specifically for two resistors. Look like this. Very similar thing. And then we can simplify this. And thus, it will also be written this way. Thus, it would be 2.75 times 10 to the power of -3 webers multiplied by 197,513 divided by 197,513 plus 228,447, and the result of the left magnetic flux would be 1.27 times 10 to the power of -3 webers. It is the final result of the left magnetic flux. So let's call this. And now we have to find the right one. exhausting for me to spell all these numbers. Two, two, eight, four, four, two, divided by two, two, eight, four, two, plus 197,513. The result is 1.47 times 10 to the power of negative 3 Webers. So we have found the left magnetic flux. We have found the left magnetic flux. So this one is the left one, and this one is the right one. And now we have to find the flux density of the left branch and the flux density of the right branch. I will have to do one last erasing. The formula to find flux density is actually very simple. It's not complicated at all. Flux density is how dense the magnetic flux is in an area. Thus, its formula is B equals magnetic flux divided by area. So to get the flux density of the left branch, it would be 1.27 times 10 to the power of negative 3 Webers divided by the area, which is 0.00545 meters squared, which we have found here. And the result would be 0.247 Teslas. For the right branch will be 1.47 times 10 to the power of negative 3 Webers by the same area. And the result will be 0.286 Teslas. So we have finished understanding the magnetic circuit. I hope this video can help whoever was interested in learning how to calculate the magnetic flux and the magnetic force and the flux density of a magnetic circuit. Yeah, that is all. As you can see, I didn't prepare for this video at all. I just wanted to stop myself. Why not just make a video of this topic, because I find a magnetic circuit very interesting. Because when we think of a circuit, we always think of electrical circuits. We almost never think of a magnetic circuit. But I've had semblances of the existence of magnetic circuits when there was a lab in my college. In the physics lab, if you see my Instagram, I have a post about electromotive force, Faraday's electromotive force, and basically there's like a table. There's like, I would say like a 30 by 30 centimeter square with a lot of magnetic coils and components. And when I look at this thing, I think to myself like, wow, this is what I think of a magnetic circuit if there is even one. And I didn't even know that magnetic circuit exists until just about a few days ago within the class of fundamentals of electrical power. So It's definitely worth it, interesting and fun to study electrical engineering, and especially areas surrounding the power and telecommunications as well, and not just the electronics. And that is all from this video. Thank you for watching. I apologize if there is anything unclear about this video, and if you have any questions, feel free to ask me. Thank you all.